Welcome back, ladies and gentlemen, to your Part B of your PN1 notes. This is where we're going to talk a lot about special properties of functions, and let's first talk about increasing and decreasing functions. Pretty straightforward as far as that goes. If you look at this first one here, when you're seeing the graph constantly increase on the y-axis, that's going to be an increasing. Here, as x is increasing, notice the y is decreasing, almost like a negative slope if you want to think of it that way, versus a positive slope, even though obviously we're not dealing with slope here. So decreasing as x increases, y decreases. And then lastly, as x increases, if y does nothing, then we have constant, a constant. It's not increasing or decreasing. So let me summarize that for a minute here, okay? So down here it says increasing, that is as x increases, the y, or f of x, which is the same thing as y, also increases. This shouldn't be here, by the way. And now, let me kind of bring this up in center. Decreasing as, and I bet you already figured this out, as x is increasing, the f of x, or the y, is decreasing. And lastly, as the x is increasing, for constant, the f of x has no change. So those are important. Part of it is vocabulary, but part of it is just as we move through the different types of functions, especially like piecewise and so on, it's important to know your increasing, decreasing, and constant, specifically getting into calculus, because with you're constantly taking derivatives and looking at rates of change at different intervals, and everything means something very specific in the physics sense with looking at parts of the function. I'm trying to simplify something that's not that simple to simplify. But anyway, extrema, those are pretty, I kind of enjoy them because they're pretty straightforward. They're points on a curve in which a change in a direction of curvature happens. So for instance, as we're going down this graph, right here before, as we were increasing, now we're going to be decreasing. This here, point P, is a inflection point. Same thing here. We went from a decreasing now to a increasing. Again, there's a reflection point. And then same thing here. We changed from increasing to decreasing. There's an inflection point. So let me kind of erase that because we're going to have to read that graph here in a moment. So looking at this, it's asking what's the local max, absolute max, local min, and absolute min. So let me just say this. The locals mean that in a small interval, is it the peak? I mean, for a max. And of course, if you're talking about local min, is it a minimum in a certain, like a small interval? Absolute max or absolute min means the all-time highest point ever, ever, ever. So let's first talk about maximum. So we have this point as a part of the peak and this part as part of the peaks. So those are both maximums. The P is going to be the local max because it's obviously not as high as R, but it is still a peak or a maximum within this smaller interval, right? If I were to cut that outside of that interval, P would definitely be a maximum. But R, by far, is the all-time absolute max, okay? So that same idea is going to happen with minimums. So the local minimum, we have this small like valley, so that's a very min. You don't have any other minimums, but something I do want to make sure you note is that if you look at this graph right here, this is continually going down, this one is continually going down. So I'd be hard pressed for you to explain to me how there's an absolute min, because this graph continues to go down to either negative infinity, or maybe it comes back up at some point that we're just not seeing. So we don't know. As far as we know, there isn't one. So none. There is not an absolute minimum because it's a constantly decreasing graph. We don't know what's happening outside of what we see. The local minimum, though, there's something different. That is going to be the Q. And now I'm kind of giving the impression that it's going to curve back up. I shouldn't do that because, looking at this, my interpretation is that it's going to continually decrease down to negative infinity. But because of that, we don't have an absolute minimum. We have a local minimum, which is Q. Okay, can you have more than one local minimum? Yes, you can. And obviously you see that you can have no absolute minimum or maximum either. So there's a lot of different little scenarios there. So now we get into kind of this graphing problem. And I want to say that you do want to throw this in your graphing calculator, and so you're not expected to be able to graph this, I guess, by just looking at it. You can figure things out, but gosh, it'll take you a while. And so I'm not insulting you all. You can create an XY table, and you can figure out zeros and all that kind of good stuff that you learned last year, and we'll be doing that. But this isn't the time for that. So use your graphing calculator to get a decent picture of this. So we have a fourth degree polynomial, and it says sketch the graph. Now, sketch does not mean give a rudimentary drawing. It means to not have to graph a million points, but I'm expecting you to actually graph the zeros and put in the max, absolute, and relative mins and maxes points. And then from there, give any extrema and the increasing, decreasing intervals. So what I'm going to do, because I can't physically show you, obviously, a graphing calculator, but I do use Desmos, and I've got to tell you, I love Desmos. And somehow I have to figure out how we can use that program eventually on assessments, but because of I hate to say, the cheating ability about getting online, we can't use them yet. If we can lock down the iPads, maybe that's a different story. Okay, so here I already typed it in. If you've never used Desmos, I got to tell you, you have to. It's about as easy as Google Classroom to figure out. DESMOS, Desmos. All I did was type in y equals x to the fourth minus 7x squared plus 6x. Literally just typed it in. Very easy. It graphs it as I'm typing it in. And what's nice about Desmos is you can really kind of zoom in, zoom out, and anywhere of interest to you, like if this point is of interest, you can click on it and it'll actually give you that point, this one as well, this one, and this one. Makes graphing zeros very, very fast. And then not only does it do that, but if you do this, it'll give you your, in this case, because you see how this graph is continually increasing, it doesn't obviously have an absolute max. It has a relative max, which is this point right here. And you would definitely want to write that point down. Now, I would always say to the nearest hundredth, 2 decimal places, but because of the space on the note guide today, I'm just going to say to the nearest tenth. Down here, same thing, and actually pre-calc, just so you know, is usually to the nearest thousandths. So we usually do everything to 3 decimal places. So don't let me make you feel like we're going to be always rounding to the nearest tenth. Actually, what's interesting is Algebra 1 and Geometry, we round things to the nearest tenth. Advanced Algebra to the nearest hundredth, so 2 decimal places. And in this class, we'll be rounding things to the nearest thousandths on most occasions. So these points are really important, and also this one way down here, look at that. So if you're in your graphing calculator, you're going to need to adjust your window, because look at this max or minimum, this is the absolute min, is way down here at negative 2.1 and negative 24.1. So with that information, you're going to be drawing your graph. So let me kind of get back into my notability. I have to figure out where it's at, though. Give me a minute. Okay, here we go. So I'm going to be graphing this. Let's see, 1, 2, 3, 1, 2, 3. I know that this is one of my zeros. This was one of my zeros, or x-intercepts, you can also say, right? And this. And then I'm going to kind of, now, of course, this is where it is kind of a sketch. I'm going to get this in pretty good, but it is definitely... I'm going to remind myself that that is 1.6, negative 1.8. So it's important that you label those extrema points. And then this one up here, right there, is 0.5. That's 0.5 and 1.3. And one last one was that one way down. Now I have to adjust my screen in general to meet this, because really we're coming way down here. Let's see, negative 2.1, and then way down here. And of course we can't graph it accurately like that, but I'm just going to write negative 2.1 and negative 24.1. Okay. By the way, this problem is the reason why I cut and went from part A video to part B video, because this does take a little bit of time, and I realize that, so the video can get obnoxiously long, and I don't like my videos being longer than 15-20 minutes. Okay, so now I'm going to graph this in here as best I can, and usually my first try is really not good, so let's just see how I do here. I can't talk at the same time. Oh, that's not good. Okay, that's pretty... Okay, I'm sure you guys are doing better than me. Of course, I'm using a stylus and a Notability, so... Oh yeah, that's pretty... Yeah, I'll take it. Of course, I completely missed this one down here, but I'll just make it bigger. Okay. So this is what I would expect you to do when you sketch a graph. You want to put in some major points. You're going to probably ask, how is, or I mean, you may ask, I know your advanced English teacher demoed this, how to find these maxes and mins. You would use your second calc button in your graphing calculator and type in max or min. So if you need me to show you how to use those graphing calculators, just ask me in class. But otherwise, in this demo, I'm just using Desmos. Okay, so local max, like I said, there's not an absolute max, so we can say that none right now. Now, I'm going to just say this, that maxes and mins are always using the y coordinate. So these are y values that we're using. And you're going to see why I bring this up. And it seems like, well, yeah, of course, Ms. Bakken, it's going to be the y values. But give me a minute here. You're going to see down here when we talk about increasing and decreasing y, we need to remember it's y values for maxes and mins. Okay, so the local max is right here. And again, we're using the y value because remember, y is moving up and down. The x is your horizontal movement. So the y max, or the local max, excuse me, is 1.3. So no absolute max because it's continually increasing, and a local max. By the way, if one side is increasing continuously, like forever, and one side is decreasing absolutely forever, that means it's not going to have an absolute min or an absolute max. It might have some relatives, or I'm sorry, relatives is another word for local, but it'll have local maxes or mins. But if one side of the graph is increasing and one side is decreasing indefinitely, then that's means that you're not going to have either absolute maxes. Okay, so the local min, well, I see we have two mins, but this one right here, let me change colors here for you. This one right here and this one right here are both minimums. Obviously, the one that is local, or not the biggest absolute minimum, is going to be, negative 1.8. Now notice I have an error in my words there. Obviously we don't want to find an absolute max again. It should have been absolute minimum. And the absolute minimum, again, is the y coordinate at that minimum point, which is negative 24.1. Okay. So that is, students tend to find that pretty straightforward. Now I will say that the number one error on the assessment, even though I say this, is that students get increasing and decreasing wrong because they're thinking about y coordinates with this local max and mins and absolute max and mins. The increasing and decreasing is always using the x coordinate, because what we're interested in is doing an interval of the movement as we go from left, or very far left on the x-axis, all the way right. So we want to see, where is the graph increasing? Now actually I turned it to purple, but let's go back to that blue. I like that blue. So right here from positive infinity, I'm going to go all the way from as if I'm reading the graph from left to right as we read. It's going to go down, 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 and if it's as x is increasing, the y is decreasing, like this is, that means it's not obviously increasing, it's decreasing. It's decreasing from negative infinity all the way, so it's going downhill all the way from negative infinity all the way to this point right here. Now this is where people screw up. They're going to say negative 24.1, but we don't care about how low it went. We just know that that's the inflection point and that's where it stopped decreasing. And that spot is actually at negative 2.1 on the x-axis. Now, here's the thing. If you use a closed bracket or a parenthesis, does not matter in increasing and decreasing. It just doesn't. So I tend to use a closed bracket, but it doesn't matter. Okay, but I will say that it does go down right to it and equaling it. But here's the reason why people kind of get a little bit weird about it, is because now, I'm going to change colors. I can go from this inflection point this way, and now we're increasing, aren't we? So remember, inflection points, oops, I'm totally missing my curve. Inflection points are where it changes from increasing to decreasing and vice versa. So I know that my graph is increasing from negative 2.1, and now notice I used a parenthesis in this case. If I used a bracket, it doesn't matter. This is not domain and range. Domain and range is very, very picky. Increasing and decreasing doesn't matter. Look, I'm going to be a rebel. I'm just going to put a bracket here. Okay? Because it does actually start there, right? It's actually equaling negative 2.1 and increasing all the way to 0.5. And it's equaling 0.5, so I am going to do a closed bracket. Now, I'm going back to blue because I'm decreasing with blue. And so I'm going from here down to this inflection point. And again, notice we're interested again on how it's moving across the x-axis. So there's no union or anything like that. All we're saying is it's decreasing. So I'm going to use a semicolon. It's decreasing from 0.5 to 1.6. And I will say this is the one where even on my note guide, instead of using 0.5, I by accident wrote 1.3. Why? Because I'm so used to doing maxes and mins. So you just have to really, really put a note to yourself on any kind of assessment or when you're doing it that these are all about the x values. These are the x values when you're talking about increasing and decreasing. Okay, and one more. Let me switch over to green. We're at the inflection point and we're going all the way up to positive infinity, starting at 1.6. Well, 1.6 to infinity. Oh, I don't know what I just did there. It keeps doing that, doesn't it? Okay, so that is a really perfect example of how you can graph and show your maxes and mins, and also talk about increasing and decreasing. Just again, be super careful about whether you're using your x values or y values. Okay, so one last idea in this note guide, and like I said, I know this is a little bit of a beast. So it's talking about continuity. Continuity is, and let me just read this right from the note guide. It says, graphically speaking, a function is continuous at a point if the graph does not come apart at that point. When you're taught this in, let's say, I think it's Algebra 1 is the first time you hear this, they say if you can draw a graph without picking up your pencil, it is continuous. That's another way you can define continuous. Now, there are all sorts of situations where it's not continuous, and that's when we have them listed down here. It says match the definitions below to the visual example. Letter A, we have this thing called removable discontinuity. So if it's not continuous, it must be discontinuous. And in this case, letter A, it's removable discontinuity. It means it's continuous except for a hole that can be plugged with a single point. Now, it can be plugged. It doesn't mean it has to be plugged, but so any of these graphs down here, so I'm talking about this one, this one, this one, this one, this one, any one of those that is not continuous, because it's missing a little hole, would be called removable discontinuity. Now I'm just going to look at this first graph here, and I'm just going to say right away, looking at it, you know, it's kind of like doing this really pretty thing, never having to pick up a pencil. I'm going to right away say, hey, you know what, that's C, that's continuous. That's this one right here, and we've already talked about that. This one right here, look at this. We're coming down, and all of a sudden, ooh, there's a crater, there's a hole, and that hole is filled up here, if it's not obviously down here, but, or it's defined up there, I shouldn't say filled in, it's defined up there, and then it kind of keeps going. So this is an example of a removable discontinuity. We talk a lot about these at the end of the year when we deal with heavy-duty limits. And it's kind of an interesting idea, and we do go back to this note guide, so it's really important that we have, you know, a decent understanding of this at this point in the game. So looking at this next one, notice it kind of comes, and again, there's a hole. Notice it's not defined there, but it just kind of, after that, it keeps on going. That is, again, another example of a removable discontinuity. This one, now there's only two left here. I'm just going to say I didn't even talk about them yet. Letter B is a jump discontinuity. It means it's a discontinuity that is not removable, which means it isn't just a single little point missing, but it is a gap that is impossible to plug in with a single point, because really, if you have a gap in any kind of mathematics, you're talking about an infinite number of points within that gap. So letter B, let's look to see. We have this one and this one to have to choose from. And since they both look like they have a gap, let's come down here with letter D and see what that one's about. This one says an infinite discontinuity. It means that it's definitely not removable. So let me just say this. Any of your hyperbolas is an infinite discontinuity, or has infinite discontinuity. This one, notice it's coming down, and it just kind of has, it doesn't have just a point missing, but it has a chunk missing, and then it comes up here. That's an example of that jump discontinuity. Now there's an infinite number of points in this space, but the reality is it's not an infinite space that's missing. Where on this last one, this is what's happening with this hyperbola. It's going down all the way to negative infinity, and then you are coming all the way up to positive infinity and coming down like this right here. Hugely different than this previous example. This one's an example of an infinite discontinuity. So that's kind of a quick summary of the different types of discontinuity, and we will be talking about those quite a bit. These are two examples that we want to talk about, and I'm just going to tell you up front that I switched this from a different format, and this example is completely wrong, like not even close to what it should be. That problem right there should be x plus 3 over x minus 2. So that is the function x plus 3 over x minus 2. Now again, you can graph it, and you'll realize very quickly that when you graph it, it looks a little different as far as how it looks. And how about we do that in Desmos really quick? Just because I didn't actually show you how to create an equation in Desmos. So let me just show you. I'm going to actually just get rid of that one that we had before, and I'm going to put in parentheses x plus 3. I'm going to close that parenthesis, and I'm going to say divided by. Notice it automatically understands that it's in a denominator now. X minus 2. So you gotta love this program. It's just so simplistic. Notice what we have there. This is definitely a hyperbola. So we've got definitely an infinite discontinuity happening. So I'm going to, and again, kind of, you know, I have the chance to talk about it. Notice that hyperbola is coming over, getting very, very close to 2 on the x-axis, but not actually touching it because we have an asymptote there. So I'm going to go back to Notability now and say, what is the name of the graph? It's a hyperbola. My handwriting. Hyperbola. The domain, well, it makes sense for all of x except for 2. It does not. I'm going to put that down here just so we remember x cannot be 2. But remember, we're doing interval notation, so we're going from negative infinity to 2, but not actually equaling it. Union. We're jumping to the other side of that 2 to positive infinity. So again, it's kind of like the lower bound versus the upper bound, and we talk a lot about that with limits later. Discontinuity at 0, at x equals 0. That's a weird question. What that means is if you plug 0 in for x, you end up with 0 plus 3 over 0 minus 2. You end up with 3 over negative 2. Is it undefined, or is there a problem there? And the answer is no. So we're okay there. So that's what that problem means. Now, the type of discontinuity in general, like if you look at the entire graph, we had mentioned is an infinite Infinite. If you want to use an infinity sign, that's fine as well. The infinite discontinuity. Discontinuity, and I'll abbreviate that. Is it removable or non-removable? You know what? It is. There's so much missing that it is not removable. The only one that's removable is if it's just a point that's missing. Okay, this one right here. If you were to graph this, you'll end up with a quadratic. The quadratic gives you a graph of a parabola. Parabola. By the way, I'm going to go back to this last example. We graphed it, so that's how we knew that it went to 2. But don't forget that powerful thing that I showed you earlier, where this down here, that number 2 rule is you can't have a or 0 in the denominator. What would cause that to be 0? It'd be 2. That's why this is happening right there. So just kind of, again, tying into last year's advanced algebra course that you had, and also early in this note guide. Okay, the domain for any parabola is all real numbers, so we're going to go negative infinity to infinity. Discontinuity at 0, well, you can put 0 in, and you know what? You get a number back, so that is going to be a big fat no. Type of discontinuity, you know what? It's a parabola. Everything's defined. There's no issues with domain, so it's continuous. And is it removable? Well, you know what? This is not applicable, so that doesn't make sense. Okay, now here's the issue. There really, I feel like there's an example missing that really would be very helpful to you. And so I'm going to do it right down here. And I would expect you to do this with me, of course. H of x equals x squared minus 4 over x minus 2. Now, when you look at it, it looks very, very complicated. I realize that. And if I were to go on Desmos and graph it really quick, and I'm going to do exactly what I did before, I'm just going to try to do it a little bit speedier here so that I'm already past my time, and I'm looking at it, and it's starting to freak me out. So, but I also know you probably want me to explain this halfway decent. So here we go. Okay, so there's that divided by, and I'm kind of moving it along, x minus 2. And there it is. Okay, so you're going to go, that's a graph of a line, Miss Bakken. And you know what? You are absolutely right. Now, if you weren't sure that was a line, you can scooch it back. Look at it. It's a line no matter what. Okay, so that is the name of the graph. Now, look at that graph really carefully. Or not the graph, but look at that equation. Rule number 2 says no 0 in the denominator. So we know instantly that x cannot equal the value of 2. But it looks to me like if we go over here, here's the x is 2. I'm going to go right up. It sure does look like 2, 4 is a value. I'm going to put my finger right on there and try to get it to go right there. Now look at 1 point. Ooh, I'm trying 1 point. Oh, look at that. Look at, oops, I don't know if you saw it, but there it's getting close to 2. I'm looking at the x coordinate close up, but when I'm actually at 2, it's undefined. It's a missing point. It just is not showing up in the graph. So there's the same thing, and come over here, and it's undefined coming from the top. So if you come from the top bound, approaching 2, it's undefined, and same thing here, it's undefined. Okay, bottom line is don't trust your graphing calculators nor Desmos because they can't. They're a finite tool, so you're going to have to use your brain here, and you need to know that x would not be defined at 2. So the first thing I'm going to put is over here. Hey, we know instantly before we touch this thing that x cannot equal 2. We know that because that would cause a 0 in the denominator. Now you might be saying, well, how is it that the graph is a line? You know, why is the graph a line when it looks very complicated? Here's what I'm going to show you. If you factor that top using difference of squares, so that's something obviously you did quite a bit last year. X minus 2, x plus 2, just factored it. Just carry this x minus 2 over. Notice we have common factor there, and you end up with x plus 2. If you were to graph that, that is a y-intercept of 2 right there, and a slope of 1, up 1 over 1. And so here is your line. And again, what's happening, folks, is that right where x is 2, here's 1, 2, this spot, it is a gap. Now, it doesn't look like a gap on the graphing calculators or Desmos, but it is most definitely a missing point. So, and I shouldn't use the word gap, I should say a missing point or a hole. So this is definitely a hole. Oh, that you can fall in. Okay. So anyway, so we have the domain is x does not equal 2. So let's kind of write that properly. Negative infinity to 2 union 2 to infinity. Notice I don't use the closed brackets in this situation. And it is definitely I all of a sudden I'm just like, what is the name of it? It's a removable discontinuity. Discontinuity. And you know what? I felt like the other two examples were good, and I didn't want to take any of those off, but I really felt like we needed to have an example of a removable discontinuity. With that said, is it defined at, what did they keep saying? X equals 0? Yeah, if you put 0 in here, it'll be defined. Is it continuous at x equals 2? Absolutely. That is where it has the hole. So if that question was altered, you would say yes versus, that x equals 0, 1. Okay, so that is the summary of all the functions that you have ever learned, and then plus some information you have probably never have seen before. This is the practice right here that you're wanting to show me that you're understanding the material. On Google Classroom are the answers, not the worked out solutions. Of course, those are going to be for you to show me, the worked out solutions, but check your answers on Google Classroom to make sure you're getting them right. Of course, we're going to go through questions in class as well. Lastly, just kind of as a heads up, there is a hard copy of textbook obviously in the class, but it is literally a 7-pound book. So on Google Classroom, I upload all of the online sections. So when you go onto Google Classroom, you are looking for section 1.2, you are going to have to scroll through, because it is the actual textbook. So you're going to have to scroll through section 1.2 until you get to the practice. And once you get to that practice, you're going to do 4 through 11, 14, 17, and so on. So if you have any questions about that, just let me know. Once you do it once, you're going to be like, yeah, okay. But it's kind of weird initially because you do have to go through all the book's instructions till you get to the practice, or what people typically like to call homework problems. Okay, well, thank you for tuning in. And again, sorry about how long that video got. And we will take any questions in class. Take care.